We did this example in the previous video, but I want to point out a couple of things. This was a case of a repeated eigenvalue. We ended up getting only two eigenvectors, and those two eigenvectors are linearly independent because one came from this eigenvalue and the other came from this eigenvalue. They're different from each other. We only got one eigenvector from this repeated eigenvalue. And I want you to notice it. When we did, here's the repeated eigenvalue. When we got it into row echelon form, we only got one row of all zeros. The rank of the A part of this matrix, well, the rank of the whole thing is 2. Remember what was it? N minus the rank is the dimension of your null space. N is 3. The rank is 2. 3 minus 2 is 1. You're only going to get one dimension of 1 in that null space. Another way to look at it, because the A's are always square now, the number of rows is the same as the number of columns. So the number of free variables is going to be how many all 0 rows you have. Try to put this all together in a little bit. Here's another example. This looks like a funny A matrix, and we're going to find another way to do this particular problem, but so far let's do it the way we did it before. This is a triangular matrix, so the eigenvalues are just the in diagonals, 0, 0, 1. So we have a repeated eigenvalue of 0. Let's do the distinct one first. Subtract 1 from each diagonal. You got a -1, -1, 0. That's pretty easy row ops. Pivot, pivot. K3 is the free variable. Got that row of all zeros, you better. Remember, you don't have to have this right column being zeros if you don't want that. This says K1 equals 0 and K2 equals 0. K3 is a free variable, just set it to 1. There is my eigenvector corresponding to that eigenvalue. Now let's do the repeated case. Remember, in the previous example, we only got one eigenvector for a repeated eigenvalue. In this case, well, this guy, just to do row ups, just move that bottom row up to the top. One pivot, 2 free variables. We have 2 all 0 rows. That means 2 free variables, 2 free parameters. And all this top row tells me is that K3 equals 0. I use the 1, 0 trick to give me 2 linearly independent eigenvectors, or basis vectors for the null space. Free variables are K1 and K2. So in one case, I'll set K1 to 1, K2 to 0, and K3 must be 0. In the other case, I set K1 to 0 and K2 to 1. K3 is still 0. I got 2 linearly independent eigenvectors from this repeated eigenvalue. The number of eigenvectors you're going to get for a particular eigenvalue is the number of free parameters. Here we had 2 free parameters. This previous example, we only had 1 free parameter. Any linear combination of eigenvectors for a given eigenvalue is also an eigenvector. These two guys are linearly independent. You can use them to generate any other eigenvector, but it won't be linearly independent of these two guys. I guess this summarized the rules. How many linearly independent eigenvectors for a repeated eigenvalue? It's the number of free parameters, which is the same as the number of all 0 rows for that repeated eigenvalue. So if A is n by n and all its eigenvalues are distinct, you're going to get n linearly independent eigenvectors, 1 for each eigenvalue. If an eigenvalue is repeated, say m times, there could be from 1 to m linearly independent eigenvectors associated. When solving for a repeated eigenvalue, the number of eigenvectors is the number of free parameters for that particular eigenvalue. I'll just leave this. You can read the rest of the word yourself. But anyway, that's how to know how many linearly independent eigenvectors you're going to get. For an n by n, you don't always get n linearly independent eigenvectors. If all your eigenvalues are distinct, yes, you will. But if one or more of your eigenvalues are repeated, you can't tell without doing more work. We'll save another couple of examples for other videos, so we'll stop that. I covered repeated eigenvalues enough.